So on your note, goodness of fit. So 11.1, goodness of fit. So here's our example. Here's number 1. You got it on your handout. Let's take a look at it. You want to see if it makes a difference which lane to be in when there is traffic. This is kind of a little bit of a funny question. In fact, yeah, let's all right, let's do this example. So what we're looking at, you randomly observe 312 cars as they pass by on the 4-lane freeway. So what we're wondering is, are all 4 lanes the same? You know, changing gears, I'm jumping to number 3 because I think it's way more interesting. Yeah. Let's do number 3. So jump into number 3. How do you test if a die is fair, like a 6-sided die? How do you take a die and test to see if it's like a cheaty die or if it's a fair die? You ever thought about that? Yeah, exactly. So if I have a die like this, right, and I roll it, don't go in the hole. And I roll it, and I roll it, and I roll it, right? And kind of keep track. Suppose this is what happens. What's on the screen there? 22 times they got a 1, 23 times they got a 2, 22 times they got a 3. So I'm jumping to number 3. You probably know where I'm at on the handout, right? So these are the different amount of times they got the different results on the die. So what's up with that? Is that a fair die? Look at those numbers. Is that a cheaty die? Is there something cheaty about that die? What do you think? Cheaty? Zach, why do you think cheaty?
Just because of number 6. It's so low.
Because there was only 5 6s that came up. Yeah, that's funny, isn't it? All the rest of the results had around 20. This 18 a little lower, this a little higher, 30. So yeah, that 6 is really low. The 5's kind of high. So, what do you think? Is that cheaty die then?
Yes.
See, you know what my question is going to be? Couldn't that have happened by random chance luck? Right? Because remember, that's been the theme of the whole course. I hope it hasn't gone by you. You've seen it, right? Everything in life happens because of random chance luck or because something causes it. And the question is something causing that die to do that? Or could that have happened by random chance luck? Is that a cheaty die that's got a secret little weight inside or something like that, thus causing that behavior? Or could that have just happened by random chance luck? You just happen to get less 6s and a little more 5s. How do you answer questions like this? This is super important to be able to, right? Much of life, much of business, much of medicine needs to answer questions like this. They got to know if something's causing that to happen, or if you got a new drug, you're giving it to different patients. Some do better, some don't do better. Seems to do a little better than the old one. Is that random luck? Or is the new drug really working? Is it really causing something to happen? Or is it just random luck, the results we got? And that's just a medical example. There could be a million business examples and otherwise. How do we answer this question? I hope you see this has been the heart of our semester together, right? Is to look at something that happens, some results, and answer the question, could that just be luck? And we don't want to just be going by our warm, fuzzy feelings that day, but we want to have what? Statistical evidence that weighs in and says, yes, that could have just been luck, or no, that couldn't have been luck. Right? And what tells us the chance it was just luck? There's one thing, it's our most important thing, that always tells us in every hypothesis test problem. What piece of the hypothesis test tells you the probability that it was just luck? Oh, don't leave me hanging, please. That is what makes me feel like what am I doing all semester if you don't know the answer to that? Right? What piece of the hypothesis test tells us the probability that the results are just luck. The what? P-value. Right? Do we all know that? You need to know that. That's probably the most important thing we've learned in this class. The p-value is the probability that the results are just luck. That's exactly that's why he's the most important part of the hypothesis test, right? He determines whether we reject the null or keep the null because he tells you the chance it was just luck. That's what p-value is. The probability that it just all happened by luck. And so if the p-value gets really, really low, right? Remember the time I was flipping the coin and I got like 3 heads, and everybody just thought I was kind of lucky. Then I got 4 heads, 5 heads, 6 heads. By the time I got to 10 heads, nobody thought I was lucky anymore. Everybody knew there was something causing that to happen, right? It was a cheaty coin. Because the chance of getting 10 heads by random luck, is so low, isn't it? The p-value, I basically did a p-value in front of your eyes. Even though you didn't know the number, you felt the p-value, didn't you? You thought, no way Mr. Heron's getting 10 heads in a row by luck. Something's causing that. Right, the p-value got really, really low. So that's what we need on this problem. We need a p-value to tell us, could this have happened by luck? Or is that super unlikely? Because if it's super unlikely, then it wouldn't be wise to believe the die is fair anymore. It'd be wiser to believe, it'd be way more likely that it's true that the die is a cheaty die if the p-value is low. So we got to calculate the p-value, don't we? So, all right, so here we go. So you have your exam 4 notes. So if you look on your exam 4 notes, I'll fast forward to them. There they are. It's way at the back. We're jumping to the back. Number 10, goodness of fit. Goodness of fit. So that's what this section is all about. The null hypothesis, the HO, every time. This will be kind of nice. You won't have to look for a claim or anything like that. The HO is the same every time for goodness of fit. The HO is observed and expected data fit each other well. Observed and expected data fit each other well. And H1, they do not fit well. So there's what we need. All right, so let's go back to it. There it is. So the HO, it's down here, huh? The HO is down here. So let's select the distribution of die rolls. It might be a little confusing for you, huh? Oh yeah. You know what? I'm jumping ahead. Let's go ahead and fill these in. What should these numbers here be? The expected frequencies. Yeah. What are they, Zach? 1/6 of what? How many times did we roll this die? 120 times, right? So if you roll a die 120 times, and it really is a fair die, even Steven die, how many times should you get a 1? 1/6 of the time, huh? So you should be able to take the 120 rolls, divide by 6, and that answer is 20, right? 12 divided by 6, 2. Throw on the 0, 20. So we should get 20 ones if that die is perfectly fair, huh? Right? 1/6 of the time you should get a 1, and 1/6 of the time you should get a 2, etc. We should get 20 for all those, shouldn't we? If the die is perfectly fair, right? 120 rolls, we should get 21s, 22s, 23s, 24s, 25s, 26s. So the question is, that's if it's perfectly fair. The question is, how well does the numbers we actually got, none of them came out exactly 20, but they came out around 20, didn't they? The question is how well does it fit? It's not a perfect fit, for sure. But how far off is it? Is it off so incredibly far that we just don't believe that could happen by luck? Or is there a reasonable chance that could happen by luck, right? Because we should have got 20. 20 of everything, shouldn't we? Right? If 1/6 of the time you get a 1, 2, 3, we should have got 20 of everything. That should be 20 times 6, our 120 rolls. But we didn't get 20 of everything. But, there's always a little bit of randomness in anything you do. You're not really going to get exactly 20 of everything, right? So there's always a little bit of randomness. But the question is this too much randomness? Could this really happen by randomness? Or is it virtually impossible for that to happen by randomness? And instead, we should believe that something's causing it. It's a cheaty die. So it's all about goodness of fit. We want to see how well do these numbers fit with these numbers? Does that make sense? This is the expected frequencies. It's what we expected to happen if the die was really fair. And this is what actually happened when they rolled the die 120 times. And the question is, how well does it fit? So HO, down here, which test are you doing? Goodness of fit. So right there, you're going to select goodness of fit. We're in the goodness of fit section. So that answer is always going to be goodness of fit on that question. And then for part C, coming down, it says, what's the null hypothesis? So the null hypothesis, if you go back to the notes, the exam 4 notes, it says that basically that it fits. And the H1 is it does not fit. It's going to pretty much be that every time. It fits and it doesn't fit. Now, how do we mean it fits? Well, what would fit? The distribution of the die rolls is uniform. That's the fit, right? They're supposed to all be the same number. That's uniform. One form, right? All the same number. So that's what should have happened. That would be a perfect fit, wouldn't it? And then H1, so it's going to, on every time you do goodness of fit, HO is going to be fits, and H1 does not fit. All right, so H1, not uniform. Not uniform, so again, HO, it fits. What fits? What we expected with what actually happened. That's what we mean fit. A fit between expected, what do we expect? To get 20 for every number, and actual. So we're talking about the fit, or the lack of fit, between what we expected to happen and what actually happened. That's always 20s, right? We're thinking it should be 20 for every number. If that die was perfectly fair, and here's what actually happened. How good of a fit is that? So HO is it fits perfectly, and H1 is it does not fit. Does not fit. Okay, degrees of freedom. We have never talked about that before, have we? We're in a whole new world now. Degrees of freedom. What is it? It's degrees of freedom. Do you see it on your sheet there? What is it? Number of categories minus 1. That's the DF, the degrees of freedom. Number of categories minus 1. See it on the exam 4 notes? Want me to go there? Go to the exam 4 notes. Exam 4 notes somewhere. There it is. Degrees of freedom, number of categories minus 1. DF. I just put DF. Degrees of freedom is the number of categories minus 1. So how many categories do we have on this one? Let's go back to our, there it is. How many categories are there? 6, huh? There's 6 different things that can happen when you roll the die. So our degrees of freedom is going to be 6 minus 1, 5. So our degrees of freedom is 5. Don't worry a lot about that. That's just something the calculator needs you to put in. All right, so it's time to go to the calculator. So this is where I asked, did y'all get my email? I sent you an email about an hour and a half ago. Basically saying, if you have a TI-83, you need me to give you a program, which I'll run around and give you real quick right now. If you have a TI-84, you're good to go. It's already got the program in it. So let's do that really quick. And I sent you the program, but it's much easier with the wire. Let me just give it to you with the wire. So what we do now is we're going to put the observed values in L1. So go back over here. Let me erase all my scribbles. Whoops, I erased everything, huh? These should all be 20. All right, so you put the observed values. It says, I'm looking at the goodness of fit thing. It says, put the observed values in L1. So that's these guys. These are what we observed, what we actually saw. So put those in L1. The expected values, put those in L2. So maybe you've already done that. So put those in L1 and L2. Okay, so L1 and L2. So L1 for the observed and L2 for the expected, what we thought would happen if it was perfectly fair, 20 for every number. Okay, L1 and L2, I'm just looking at the notes. And then it says, Oh, yeah. So then we go to, now, I have different instructions for the 84 or 83. Y'all see that? So we put the observed values in L1, calculate the expected values, and put those in L2. This is just how to calculate the expected values. We already did that. We don't need to worry about that. So now come on down to, if you have a TI-84, you're going to go stats, test, and that thing right there. That's already on your TI-84. And if you have the TI-83, and I just gave you the program, you hit the program button. Where's the program button? That's right in the middle at the top. 3 rows over, 3 rows down. PRGM button, hit the program button. Find the little program I just gave you, the chi-squared goodness of fit. That's the chi goodness of fit. That X is actually a Greek letter called chi. But anyway, so do the chi-squared goodness of fit and hit enter. And it'll crank it out. For the TI-84, you got to go to the chi-squared goodness of fit test. Observed is L1, expected is L2. Degrees of freedom will be 5 because it's 6 minus 1. You don't even need to do that with the program. It just handles it automatically. Either way, so I'll do that too. Stat, goodness of fit. It's way down, for the TI-84s, it's way down on D, isn't it? And L1, L2, degrees of freedom 5. Calculate. You getting it? I'm getting chi-square equals 17.3. That's what goes right here. We're used to having T or Z, aren't we? This is a whole new world, as Disney says. This is a whole new world here. Chi-square is our test statistic now. It's not T, it's not Z. That's a Greek letter, but anyway, you can just call it X if you want. I don't care what you call it. But it's a Greek chi is what it is. Chi-square. So anyway, it's the 17.3. Actually, we don't do anything with it. Who cares? And then the p-value is what we really care about, right? Oh, we're supposed to go to 3 decimal. Oh, that's all it was. And then 4 decimal places on the p-value. I'm getting 0.00396. So that'll round to 40. 396 rounds to 40. 0040. There's our p-value. What's p-value mean again? Probability of rain tomorrow. No. Probability of?
Randomness.
Probability of randomness. Probability that just happened by luck. So is there a very good chance this happened by luck? No, that's super low. In other words, these weird results, just like we thought, that's super low. That's not very likely to happen by luck. In fact, what's the chance that'll happen by luck? 004. That's 4 in 1,000, isn't it? That's tens, hundreds, thousands place. 4 in 1,000. So you roll those dice 1,000 different, you do the 120 rolls 1,000 different times, and only 1 in 1,000 will you have in numbers like this. This is super rare. It would not be wise to believe this happened by luck. Something's causing that. Something's causing that to happen. That die is a cheaty die. Does that make sense? There is strong statistical evidence that die is a cheaty die because the chance of luck is so low. So the p-value, so you know what we do with the p-value, right? We always compare it. So I'll write it over here. 0.0040. We always compare it to what? Significance level. Yeah, what's the significance on this one? Oh, yeah, there it is, huh? Significance is 0.01 back in the first part. So significance level 0.01. And if you want to add 2 zeros just so they both have 4 decimal places, 40 is way below 100. So the p-value is low. P is low. HO must go. Go away, that is, huh? So I go up and I cross out HO. I say, no, it doesn't fit. That's not a fit. That die is not fitting with what a normal die, a fair die, would do. We believe H1 does not fit. Oh, evidence is strong, right? You know the weak, strong thing. That's still the same. That'll never change. So there's strong evidence that die is not fitting what a fair die would do. There's strong evidence that die is a cheaty die. That's the kind of die by which you can get, in big trouble at the casino. It's a cheaty die. There's statistical evidence that die is a cheaty die. Right? That makes sense? So we can come on down and answer their questions. The p-value is... It wants to say less than the alpha, the significance. Based on this, we should reject the null, right? Thus, our final conclusion, what is our final conclusion? Is there sufficient evidence or not sufficient evidence? Strong, sufficient, right? Remember, we rejected the null, we rejected the weak, so we kept the strong, right? So, strong, sufficient, so it's either one of those two sufficient ones to conclude that the distribution of die rolls is uniform? Is it all the same? No. There's sufficient evidence to conclude that the die rolls are... Oh, okay, I don't like either one of those. The sufficient evidence to conclude the distribution of die rolls is not uniform. There we go. They gave us 5 options. Not uniform. Right? That die is not going to give a fair shake to each number. Not uniform. There's something cheaty about that. There's strong evidence that die is cheating. So that's a goodness of fit test. Does that make sense? How are we doing? We good? Questions I can answer? This one looks interesting. So question number 6. It's basically saying, are men in California weird? Because here's the national averages. They're saying in the nation, the marital status of the male population age 18 and over, so men age 18 and over, 32.7% have never been married. 54% are married, really more than half? Oh yeah, of all men over 18, that makes sense, yeah. I'm getting confused, yeah, because that includes men that are in their 30s and 40s and 50s, yeah. I'm thinking 18-year-old men, but yeah, no, they're not, yeah. Widowed, 2%. Divorced, 10.5%. So that's the national averages for men, 18 and over. Now, they did some kind of survey in California to see how California men fit the whole United States. They sampled 1,692 adult men from California. And here's what they found out. 556 had never been married, 929 were married, 13 were widowed, 194 were divorced. The question is, does that fit well with the national averages? Are men in California, their marital status anyway, does it fit well? Is it typical? Or is it different? Is it extremely different? Is California different? Does it fit well with the national averages? So, here we go. So, first thing we got to get is the expected frequency. So, I'm doing number 6. So, how do we get these expected frequencies? Yeah. Because we expected for married, the first one, or never married, first one, the never married, we expected 32.7%, right? Because that's what it was for the national average, 32.7. So I got to turn that into a decimal, 0.327 of all the men surveyed. How many men were surveyed? 1,692. And what does of always mean in math? Times, yeah, times. So just take 0.327 times 1,692, and you get 553 point. We'll just use all the decimals, I guess. 284, just better. We expected 553.284 men out of the survey to have never been married. Did the actual results come out kind of close? Pretty close. So far, the California men are looking pretty normal. They're fitting the national average pretty close. So just go through each of the categories and do that for each one. Married, 54.8. So take 0.548 of the 1,692, which again means times. And I'm getting 927.216. Pretty close to what happened in the California survey. Next category, widowed, 2%. So that's 0.02, right? Be careful there, 0.02. Times 1,692. And I'm getting 33.84. And finally, last category, divorced. 0.105 times 1,692. I'm getting 177.66. That one's a little further. The last two are a little further off than what we'd expect, but not huge. I bet this is going to be a pretty good fit. We'll see. When we get to I think it'll be a large chance that this is just luck. I'm betting in a high p-value. We'll see. Is that good? So you see how we got those? So now how do we do the goodness of fit test? Or down here it's asking us what kind of test? Well, goodness of fit. We're in the goodness of fit section. Of course it's goodness of fit. HO, so what's the null hypothesis there? Remember, so if you look on your exam 4 notes, let me go over there with you. It's right there. Exam 4 notes, the HO for goodness of fit test is always that they fit each other well. The observed and expected fit well, and the H1 is they do not fit well. Every time. Never changes. It's kind of nice. It's kind of like saying, remember HO is always equals? That's like another way of saying equals. They fit, they're equal, they're the same. It's like another way of equals, huh? And H1 is not equal. They don't fit, basically. So, HO is they fit. So which one of those basically says they fit? The same as as nationally, huh? California is the same as the nation. And which one of the H1s say does not fit? Is not the same. Yeah, not the same as the national thing. Easy enough so far? These are pretty much the same every time. Good. Next screen, if you're good. Next screen. Oh, we already had that one. There it is. Okay, degrees of freedom. How many degrees of freedom on this one? 3, because it's number of categories. Yeah. Number of categories minus 1. Yeah, so it'll be 4 minus 1, 3, huh? Because there are 4 categories. Never married, married, widowed, divorced. So 3 degrees of freedom. So now it's time to go to the calculator. You know what to do, right, according to the notes. So we put the this data right here in L1. These numbers, just use all the decimals. We'll go in L2. And then we do our goodness of fit thing. All right, you guys get it? So you put the data in L1 and L2 and do the chi-square goodness of fit. And we got this number is 14 point, once 3 decimal places, 3537, so 354. And the p-value, it is kind of low, huh? It's lower than I thought. 00246, so 25, 0025. So actually, that means it's not a very good fit. So that p, what level do we test at? The significance? 01. So 01 is the significance level. So what do you think? Is that p-value below or above? Yeah, if you add the 2 zeros, just so they're more easily comparable, that's the number 100, and that's the number 25. 25 is below 100, huh? Yeah. So the P is low. I'm wrong. The P is low, so the HO must go away, like usual. What was the HO? The HO was that they fit, and H1 was they do not fit. And it's the weak, strong evidence thing, like usual. It always is. So weak evidence for the HO, strong evidence for the H1. So the HO must go away. So we reject the null, cross out the null, we keep the H1. So we have sufficient evidence to believe they do not fit. That California men are different than men in the nation, especially because of the widowed number and the divorced number came out different, I guess. We don't believe that's by luck. We believe that California men are different. There's something causing that, something causing different behavior in California men from the rest of the nation. There's only a 0.025 chance that happened by luck. So it's not likely. So is that good? So you can answer all those questions probably. So what's the last question here? The final, so right here we reject the null, and we said there is sufficient evidence, right? Strong evidence. So get rid of that insufficient. It's not those guys. It's one of the sufficient ones. Which one? Sufficient evidence to conclude that the distribution of marital status in California is not the same. Yeah, exactly. That's it. Not the same. What do the other ones say? It says are dependent. No, we're not doing that. It says it is the same. No, it's not the same. It doesn't fit, right? Our conclusion was does not fit. Strong evidence does not fit. Good? That's easy enough? Not too bad? Kind of the same every time? Shall we go back then? So I skipped. What did I skip? The boring ones. Do you want me to go back? I don't like the boring ones as much. We can go back to number 1 if you want. What's 2? 2 looks a little more interesting to me. Let's do number 2. How about? Number 2. Are phone calls equally likely to occur any day of the week? You think? Do you get the same number of phone calls Monday through Sunday? Yes, I guess it'd be if it's business or, it's probably depend on the use of your phone and everything. Anyway, whatever. It's kind of a weird question, really. So let's just go through and crank it up. What do they want us to do? They say, are they equally likely? So equally likely means the expected numbers, we're supposed to do them just like we did the dice example, meaning equal, all the same. Remember how that was 20, 20, 20, 20, 20 for the dice one? That's what we're doing here. We're saying, hey, basically, are these all going to come out equal? Are they all going to be equal? So, how many did we do total? 357 randomly selected phone calls. So, if the 350 say they grabbed 357 phone calls at random, if they're coming out equally likely for the different days, then it should be 357. How do you figure out how many should be on each day? Just divide by 7, right? 7 days in a week. So, is that what it is? 51? So all these then should be 51. Should be 51 per day if they really are equally likely. See how I'm coming up with that? I got that from the phrase up here, equally likely. So we're seeing how well the observed fits with what we expect. If they're equally likely, we expect them to all be 51. So now put it in L1, put it in L2, do a goodness of fit test. Isn't this easy? It's just the same thing every time. So, we're supposed to go through, what test are we doing? Goodness of fit. Goodness of fit. What's the HO? The HO is always that they fit. And the H1 is that they don't fit every time. So which one of those really says fit? Uniform, right? Calls, distribution of calls is uniform. And so now put these in L1, put these in L2. And then let's do goodness of fit test. What's the degrees of freedom? Yeah, degrees of freedom is 7 minus 1, 6. Right, because it's number of categories minus 1. So HO is that they fit. H1 is always that they do not fit. Do not fit. So, do they not fit? I don't know. I'm trying to figure out the H1. Which one? This is H1 here we're trying to do. Which one of those? Is not uniform. So they don't fit the uniform pattern. That's H1. All right. So let's crank it on your calculator. I just cranked it out. Oh, no, I didn't. I'm about to. Let's crank it out. And there I did it. Okay, so I'm getting the chi-square. This is 18.196. Y'all getting that okay? 18.196. And then the p-value is 0.00576, so that'll round to 5.8. All right, so the p-value, 0.0058. Let's compare that with the significance level. What was the significance level? Oh, there it is, 0.10. Significance level, it's back in the beginning of the question. So the significance level, 0.10. So is the p-value above or below? Below, right? If you add zeros, so they're easily comparable. 58 is way below 1,000, huh? So the p, again, is low. This is 3 in a row. The p is low. The HO must go away. The null must go. So let's go up and cross out the null. Bye-bye, null. And they do not fit, and there's strong evidence for H1. Strong evidence that they don't fit. So there's strong evidence that you don't get the same number of calls every day. It doesn't fit that, does it? So there is sufficient, so we cross out the insufficient. There is sufficient evidence that the phone calls are not dependent. Sufficient is uniform? No. Sufficient is not uniform. There it is. There's sufficient evidence that the number of phone calls per day is not uniform. Right? It doesn't fit the same number every day. So this is kind of nice. It's the same thing every time, isn't it? You don't have to work hard about what the claim is and greater or less. It's always the same. The claim is always fit. The HO is always fit, and the H1 is always does not fit. Just every single time. The rest of Chapter 11 is like this. What I mean is the HO is always one thing, same thing every time. H1, same is opposite of it. Every time. It's kind of nice. Chapter 11 is nice that way. We good there? Is that okay if I just leave the rest to you? So I did, number 2 and 5 and 6 or something? So the other 3 are pretty much the same, and they're more boring. So I'll leave those.